Okay, so you got root 2 cis pi over 5, and they want to do this multiply by itself 10 times. Let's have a look at what this is. First of all, if I expand it a little bit, cos, what's that, pi over 5 plus I sine pi over 5. First of all, it's not a known angle, so it'll be difficult to put it in Cartesian form. And that's the power 10. What quadrant is this one in? Pi over 5?
Wait. What was it in the first one?
I think it's just here. It's just like some small angle here, pi over 5. I know the modulus is root 2. Okay, and it's somewhere there. So what happens if you keep multiplying it by itself? We did look at this before. It's going to be some form of rotation. And should form a spiral, yeah, if it's not one. Yeah. Okay. But I can now use the fact that I know how to multiply complex numbers to my advantage. To multiply 2 complex numbers, I multiply the modulus. What happens if you multiply it by 3 complex numbers? So if I had, you do Z1, we had this R1 cis pi multiplied by R2 cis lambda or whatever it is. We end up multiplying the moduluses and adding the arguments, yeah. What happens if then there was a third one? Yeah, so you could get the answer to this and then multiply it by that, which would end up just being R1, R2, R3 in front, and then add theta plus that one, and so on, to infinity. If we multiply by a fourth one, we would multiply by the fourth modulus and add the fourth argument. So we're just applying that down. To the power of 10, if it's the same one, how do you think we can shorten this system down? To the power of 10, it's the same. So this root 2 is going to end up being multiplied by itself 10 times. There's a shortened way of writing that, isn't there? Root 2 to the power of 10.
Well, it's actually 2 to the power of 9. Right now, that's
No. Might be 2 to the power of 5, maybe. And what about a repeated addition? So if we want to repeatedly add the same thing, what do we do? Multiplication, yes. So I'll go back to cis, and it's going to be 10 times pi over 5 instead of writing it out. So that's that applied in. The 10 has been applied to both the... So we've repeatedly added the argument here 10 times, and we've repeatedly multiplied the modulus 10 times. Repeated multiplication is a power, repeated addition is a multiplication. What does this look like when it's done? Well, root 2 to the power of 10 is, 2 to the power of a half to the power of a 10, which is 2 to the 5, which is an actual number. What's the number? Yeah, I think it's 32. So that's our modulus. What's our argument? Cis 10 pi over 5, if you want to slow down the... What's that simplified? Cis 2 pi, okay. That's cos of 2 pi plus I sine of 2 pi. Where's that? Where's that? If I were to switch it to Cartesian, I can get a value for this. Where's 2 pi?
Wait, so how come it would be negative? How come it's cis 10 by pi over 5?
It's repeated addition. So if I multiplied it by itself once, I just add pi over 5 plus pi over 5, which would be 2 pi over 5. But I need...
Just 10 times?
Repeated addition 10 times is multiplying by 10. Yeah. So where does this sit? 2 pi, if you've just gone around, you started here, this is where you are, somewhere on this line, yeah? So what's cosine of that? What's cosine 2 pi? Is this a separate question? Cosine? Cosine? 1, yes. 90 degrees and 270 degrees would be 0 for cosine. So, and sine of 2 pi is 0. Sine, yeah, think about it. It's here, it's this point. What's that point? It might be 1 on x, 0 on y. Sine is with the y-axis, cosine is the x-axis. All right, so 1, 0. So what's the answer to this whole thing? No, 32. So 32, 1 plus 0i. So 0i doesn't matter. So the answer is just 32. So this is rotated so much around that when it finishes its multiplication, it just ends up way over here at just 32. It spins out and out and out and finishes here at 32 on the real axis. Ryan's lost.
Amazing.
No. Okay, we'll do another one. Okay, try the second one. I'm going to do the second one slower. You try and do the second one yourselves. Yeah, you just end up with a negative power here.
How do you think that works? Keep subtracting.
And then multiplying by a negative 19. So switch it to this form first. That's your challenge. And then it'd be negative 19 here, so just apply negative 19, negative 19. Yeah.
Is it 1 plus 0i?
Yeah. Because sine 2 pi, and you can check that on your calculator if you're not entirely sure, is 0. This second one is going to be a decimal modulus, because it's going to be it'd be 1 over 2 or whatever. It mightn't be 2. 1 over something to the power of 19. It's going to be 0. I don't know. I'm not saying what the modulus is. I want you to work it out. The modulus could be 2, yeah. I just don't want to tell people what an answer is. Well, don't do that. Well, before I can repeatedly multiply this, I need to get the modulus argument of it. Sketch it first. Slow down. Sketch it. Root 2 on the real axis minus root 2. It's down here somewhere. This is our complex number. This distance is root 2. This distance is root 2. Modulus.
2.
Root 2 squared plus root 2 squared square rooted. 2 plus 2 is root 4, which is 2. Very good. What's the argument?
Yeah, how do you find 2 to the power of 9? Argument is...
That's why I say it's a calculator, it's a decimal answer.
It's just 1. Root 2 over 2 is 1, so it's sine pi over 2.
You already know it's not sine pi over 2.
Oh, yeah. Oh, I know how, but like why?
This is, again, an isosceles triangle, isn't it? That angle's the same as that angle. Has to be pi over 4. 45 degrees. Root 2 over 2, sine root 2 over 2 if you want. Okay, so this is 45 degrees. So to write as a complex number, or in polar form, root 2 is not root 2, 2 is the modulus. If you want to write it cis form, negative, yes, because of where it sits. And now I got to apply negative 19 to that.
1, 0, 4, 8, 5, 7, 6. No. It's 5, 2, 4, 2.
Oh, it's half of it. I went too far.
He went to 20.
All right, so this is going to be 1 over 2 to the power of 19, which, yeah, it's just a mess of a number. I'll slow that down. 1 over 2 to the minus 19 first.
What was it? You mean 2 to the minus 19 first, which becomes 1 over 2.
Yes, I do, yes. This is going to be cis.
I assume, like, if we get this question on the exam, leaving it as 1 over 2 to the 19
You can't even
is fine.
simplify the angle, can you?
Hmm?
Like the angle is just 19 pi over 4 because there's no simplifying
It would be in the same position as this different angle.
What is 800?
Do I have the answer for this?
So do you want us to find the exact angle?
I want you to find it back in Cartesian form, if
Back in
that's...
Cartesian form.
So if the question is given Cartesian, usually they ask for it back in Cartesian,
Okay.
which makes it a little bit trickier.
They asked for it back in Cartesian?
Even if they didn't, I can't remember what the question actually was in this case. I want you to do it.
I'm using a calculator.
Yeah. Leave this as just out front. I want you just to do this bit in this bit. This, yeah, okay, just leave it as, because it's an awful fraction. So how do you convert this bit back into Cartesian?
This is an infinitesimally small number.
This is infinitesimally small, but what's this?
You just take the 19 pi over 4 cosine slash sine and then multiply it by 1 over 2 to the 19.
Okay, but how? What is
Put that in a calculator.
without a calculator? Can you do it?
Oh,
Yeah.
Good luck.
No, it's not good luck. It's
Not bad, is it? You just do pi over
what quadrant is it in?
bottom.
Well, no, if you do the math, 3, 4, if you do 4 by 4, you have 3 over 4 left. So 4 pi, 4 pi plus 3 pi over 4.
What quadrant is it in?
So 4 pi is for 3 rotations, and then 3 over 4 pi is first quadrant. Wait, what? Oh, yeah, yes.
Yeah, 3 pi over 4 sits here. So what you did was 19 pi over 4. Okay, how many times have I gone around? Well, 8 pi over 4 is once. 16 pi over 4 is twice. I'm left with 3 pi over 4 in the third rotation, which means I stop here. That angle is 3 pi over 4. That is my principal argument, or the one I can use. So what's the sine and cosine of that?
That's a good answer. I mean, good point.
So 1 over 2 to the power 19.
Well, just think about it. 3 over 4 is how many degrees? 180.
What's cos 3 pi over 4 and I sine 3 pi over 4? What's the convert it back into Cartesian? What's the known angle?
It's like 45.
So this is 45. That's 45 degrees from your GCSE. What is it? Root 2 over 2, yeah. But make sure you have the signs right. The first one's negative, the second one's positive. Okay, yes, but
This is just pi over 4 minus pi. I mean, pi minus pi.
negative root 2 over 2 plus I root 2 over 2. Positive.
It's the same thing. No, pi minus pi over 4.
Because this is the reference angle you may have used in GCSE. The reference angle here is pi over
I
4.
don't think we did this in GCSE.
The quadrant here is all sine is positive, cosine is negative, tan is negative in that one. So sine is positive, and that's negative. No, it's that. 0? Well, it's pretty close to 0.
It's definitely almost
The,
0.
the modulus is really small. So this diagram is way off because the modulus is like that.
It's almost 0.
Yeah. Hi.
I don't really get what you did on the side.
1
Pi
over 5, 2, blah, blah, blah.
Hmm?
down to 8 pi over 4.
Oh, I was saying, right, this is the angle this multiplication gave me because we were going round and round and round so much. We went around a few times. So one way around, that's 2 pi, isn't it? 8 pi over 4. I just used the same denominator here. And then the second time around, 4 pi is that. So that's twice around. And on my third time around, I have this much left over from my 19. Yeah. Okay.
So when it's 3 pi over 4, it means that's like the angle towards the smaller angle is pi over 4.
Smaller one is the one you use because it's the one you have the known angles for.
Because you know what
The sine, cos, tan thing.
Oh, I mean using pi over 4 that I don't know if it's
Yeah.
well 3 pi over 4 would
Pi over 4, it's a direct reflection. This is pi over 4, so that point is in line with that. The x value would just be negative. And it has the same y value.
Right. We're just looking.
So negative root.
The part where the pi over 4 is the part that we're looking for.
Yes.
Sir, how come, oh, so you want
The position doesn't move, we just use the pi over 4 angle. Yes.
Yeah, that's just the angle that we have that we use the 3 pi over 4 to get to figure that out.
Well, 3 over pi over 4 is actually where it sits, yes. And we use the pi over 4 to figure out what that is as a fraction or decimal. If we don't have a
So
calculator.
like 3 pi over 4 is the exact same as pi over 4. It's just pi over pi over 4.
It's the exact same, yeah, it has the same ratio. Same ratio. It creates the same triangle, yes. Okay. What we've just done is something called de Moivres or de Moivres or de Moivres. My French is awful. Is this. So if you want to just put that in.
You have to really make the name fancy.
I know, this is, I think when I de Moivres, I don't know, I don't do French.
But only a power angle is actually like if it's like a 2 power angle,
De Moivre. I'll ask Mr. Seb. So if you have this power outside, so we had 10 in the first example, it just is the same power for the modulus, and then it just multiplies the angle. So whatever it is, it ends up multiplying the angle. Yep.
Is this in here?
Yeah, it is, yeah.
Yes.
Yeah. But now we know how to use it, maybe.
So we'll give us this, but not that sign cos tangent.
I know, yeah. Yeah.
The E is actually 7.
So, interestingly enough, when, and this could be something you investigate in your IA, maybe, when we, yeah,
That's starting in like October.
no.
yeah, okay, yeah,
Well, then we're gonna talk about.
I'll talk about it in a minute. I'll talk about it in a minute. Notice that the first one we multiplied by to the power of 10, and it rotated, I can't remember what the angle was, but let's say it rotated this way and it ended up way over here eventually.